The sun is getting brighter, 1% every 100 million years. It sounds like nothing. But within a billion years, that slow, invisible increase will boil the oceans off this planet, strip the hydrogen from our atmosphere atom by atom, and turn Earth into a molten hellscape indistinguishable from Venus. And that happens billions of years before the sun even becomes a red giant. When it does, it will swell to 256 times its current size, swallowing Mercury and Venus whole and reaching toward Earth with superheated plasma. A thermonuclear detonation inside its core will briefly rival the energy of the entire Milky Way galaxy. It will tear itself apart and create one of the most beautiful objects in the cosmos. And then, over trillions of years, its corpse will crystallize into a diamond the size of Earth and go dark forever. Tonight, we follow every step of that journey. And along the way, we discover something almost no one talks about. While Earth burns, the frozen moons of Jupiter come back to life. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight, we are going somewhere. Most science documentaries refuse to take you. Not to the edge of the universe. Not to the beginning of time. We are going to the death of the sun. And not the distant, abstract 5 billion years from now version of that story. The version that is happening right now. Because the sun is not waiting to destroy us. It is already doing it. Slowly, invisibly, 1% brighter every 100 million years. And by the time it is done, it will have boiled our oceans into vapor, stripped the hydrogen from our atmosphere atom by atom, and turned this planet into something indistinguishable from Venus. A molten, suffocating wasteland where nothing can survive. And that will happen billions of years before the sun ever becomes a red giant. But the horror does not stop at Earth, because the sun itself is dying. It is poisoning its own core with helium ash. And when the fuel runs out, it will swell to over 250 times its current size, swallowing Mercury and Venus whole, and reaching out toward Earth with fingers of superheated plasma. What happens next involves a thermonuclear detonation inside the sun's core, so powerful it briefly rivals the energy output of the entire Milky Way galaxy. It involves the sun tearing itself apart layer by layer, creating one of the most beautiful objects ever observed in the cosmos. And then, over timescales so long they make the age of the universe look like a heartbeat, the sun's corpse will crystallize into a diamond the size of Earth and go dark forever. Over the next 2 hours, we are going to follow every step of that journey, from the slow roasting that has already begun to the final silent darkness that waits at the end of everything. And along the way, we are going to discover something that almost nobody talks about. While Earth burns, the frozen moons of Jupiter will come back to life. Chapter 1. The sun is already killing us. There is a number that should terrify you. 1%. That is how much brighter the sun gets every 100 million years. It sounds like nothing. It is everything, because that slow, imperceptible increase in luminosity has been running for 4.5 billion years, and it will not stop. The sun is 14% brighter today than it was when life first appeared on Earth. It will be 40% brighter 3.5 billion years from now, and long before it reaches that point, the consequences for this planet will be catastrophic. Within 1 billion years, roughly, the sun's increasing brightness will push Earth past a critical threshold. Surface temperatures will climb to around 47 degrees Celsius globally. That is 117 degrees Fahrenheit, everywhere. Not at the equator during a heat wave. Everywhere, all the time. The oceans will not boil overnight, but something far more insidious will happen. The atmosphere will enter what scientists call a moist greenhouse state. Water vapor will saturate the stratosphere, rising to altitudes where ultraviolet radiation from the sun will split the water molecules apart. The hydrogen, being the lightest element in the universe, will escape into space, and it will not come back. Earth will lose its water to the vacuum of space, not in a dramatic flood or an explosion, but in a slow, silent hemorrhage that takes millions of years. The oceans will thin, the rivers will shrink. The water cycle that has sustained every living thing on this planet for 4 billion years will stutter and fail. In 2018, Keming Jung, a researcher affiliated with the University of California, San Diego, and the University of California, Berkeley, was part of a body of work that put the timeline into sharp focus. Planet Earth will only be habitable for around another billion years, at which point Earth's oceans would be vaporized by a runaway greenhouse effect, long before the risk of being swallowed by the red giant. Let that settle for a moment. The sun does not need to become a red giant to end all life on Earth. It is doing it right now. The countdown has already started, and no one alive will ever notice, because the process is so slow that 1 million human generations could pass without detecting the change. But the change is there. It is measurable. It is inevitable. And it is accelerating. Now let us look further ahead, because if 1 billion years is the death of complex life, what comes after is the death of the planet itself. In 2 to 3 billion years, Earth's magnetic dynamo, the churning liquid iron core that generates the magnetic field protecting our atmosphere from the sun's radiation, may cease to function. The magnetosphere will collapse. Without that invisible shield, the solar wind will begin stripping the atmosphere directly, peeling it away layer by layer. Charged particles from the sun will bombard the surface without resistance. By 3 to 4 billion years from now, the transformation will be complete. Earth will enter a full runaway greenhouse. Surface temperatures will soar past 1500 degrees Celsius. That is hot enough to melt rock. The surface will glow. The oceans will not merely be gone, they will have been disassembled atom by atom and scattered into space over billions of years. What remains will be a planet choked by a crushing carbon dioxide atmosphere, a surface of molten and semi-molten rock, and temperatures that make Venus look temperate. And here is the detail that makes this truly horrifying. This is not some alien planet we are describing. This is Earth. This is the planet where you are right now. The planet where every forest, every ocean, every city, every person you have ever known exists. And in the deep future, it will be indistinguishable from Venus. The same suffocating atmosphere, the same crushing pressure, the same volcanic desolation. The parallels are not poetic, they are chemical and geological. Earth is on the same trajectory Venus followed billions of years ago. We are just earlier on the clock. Plate tectonics will stop. Without liquid water to lubricate the movement of tectonic plates, the geological engine that has recycled Earth's crust for 4 billion years will cease. The carbon cycle, which has regulated the planet's temperature by pulling carbon dioxide from the atmosphere and locking it in rock, will end. The thermostat breaks, and once it breaks, there is no mechanism left to cool the planet down. The heating becomes a one-way street. So who survives the longest? Not us. Not any complex life. The last holdouts will be microbial extremophiles, organisms that live kilometers beneath the surface in deep rock fractures, fed not by sunlight, but by geothermal heat. These are creatures that have never seen the sky, never felt the wind, never needed the ocean. They exist in a world of hot rock and chemical energy, and they will persist long after everything on the surface is gone. But even they have a limit. By 2.8 billion years from now, even polar temperatures will exceed 149 degrees Celsius, 300 degrees Fahrenheit, at every latitude. At every depth that is accessible to liquid water, the deep biosphere will cook. The last living thing on Earth will probably be a single-celled organism, alone in a fracture in hot stone, in a world with no ocean, no breathable atmosphere, and a sun that looks 40% larger in a sky that glows with heat. It will not know it is the last. It will not know what it is losing. It will simply stop. And 4 billion years of unbroken biological continuity will end, not with a bang, not with a whimper, with a temperature reading that crosses a threshold. This is the real horror of the sun's slow death. It is not dramatic. There is no explosion, no asteroid, no sudden catastrophe. It is an oven set 1 degree higher every 100 million years. And everything inside it, every living thing that has ever called this planet home, will be cooked out of existence so slowly that no generation will ever see it happening. But the slow death of Earth's biosphere is only the beginning, because the sun itself is dying. And what comes next makes the boiling of the oceans look like a warm bath. Chapter 2. The engine breaks. Every second, the sun converts 600 million tons of hydrogen into helium through nuclear fusion. 600 million tons every single second. It has been doing this for 4.5 billion years, and it will continue for roughly another 5 billion more. But here is what most people do not understand about that process. Every second of fusion leaves behind waste, helium ash, and that ash is slowly, imperceptibly poisoning the star from the inside out. To understand what is happening, you need to understand what the sun actually is. It is not a ball of fire. It is a controlled thermonuclear explosion held in balance by 2 opposing forces. Gravity, which wants to crush the sun into the densest possible point, and radiation pressure, the outward push of energy released by fusion in the core, which wants to blow the sun apart. For billions of years, these 2 forces have existed in a delicate equilibrium. Gravity squeezes, fusion pushes back, the sun holds steady. But the equilibrium is not static, it is shifting, because every atom of helium that fusion creates is heavier than the hydrogen it replaced, and it does not fuse at the temperatures currently in the core. So the helium just sits there, accumulating, making the core denser, making it heavier, and as the core gets heavier, gravity squeezes it a little bit tighter, the core contracts. And when it contracts, it heats up. And when it heats up, the fusion rate increases. And when the fusion rate increases, the sun gets brighter. This is not a future event. This is happening right now. The sun's core is currently around 15 million Kelvin and approximately 150 grams per cubic centimeter. That is denser than lead, denser than gold. The center of the sun is so compressed that a single thimble of core material would weigh more than a car. And with every passing second, as more helium accumulates, that density increases. The temperature climbs. The sun brightens. It has already grown 14% more luminous since it formed. It is measurably larger than it was when the dinosaurs were alive. The sun you see today is not the sun that shone on the first life forms. It is a hotter, brighter, more dangerous version, and it is still getting worse. Now let us fast forward. 5 billion years from now, the hydrogen fuel in the core is exhausted, not diminished, not running low, gone. The last hydrogen atoms in the sun's core fuse into helium, and for the first time in the sun's life, the engine that has powered it since birth goes silent. The core is now a ball of inert helium, incredibly hot but producing no new energy. And without the outward push of radiation pressure, gravity wins, instantly. The helium core begins to collapse. Not slowly, not over millions of years. The collapse is rapid and it is violent. As the core compresses, temperatures spike. And something dramatic happens in the thin layer of hydrogen still surrounding the dead core. It ignites. Hydrogen fusion reignites, but not in the core, in a shell around the core. This hydrogen shell burning is deeply unstable. The shell is thin and under enormous pressure, and it burns hotter and faster than the core ever did. The energy output is ferocious, and it floods outward into the sun's upper layers. The sun's outer envelope, bombarded with this sudden torrent of energy, begins to expand, not gently, in surges. Like a dying heart pounding erratically, each contraction of the core dumps more energy into the outer layers, and each surge pushes the envelope further outward. The sun begins to bloat. First, it doubles in size. Then it grows to 10 times its current radius. Then 50 times. Then 100 times. And it keeps going. According to calculations by Klaus Peter Schroeder and Robert Conan Smith, published in the monthly notices of the Royal Astronomical Society, when the Sun reaches its maximum expansion on the red giant branch, it will have grown to approximately 256 times its current radius. 256 times. Today, the Sun is about 865,000 miles across. As a red giant, its surface will extend out to roughly the current orbit of Earth, 1 astronomical unit. The distance that right now separates us from the Sun will be inside the Sun. As the outer layers expand, they also cool. The surface temperature drops from the current 5,800 Kelvin to around 3,000 Kelvin. The Sun turns red. Not the warm, inviting red of a sunset, a deep, ominous red, the color of cooling metal. Per square meter of surface, it is dimmer than it is today. But because the surface area has increased by tens of thousands of times, the total luminosity of the Sun skyrockets. It will be thousands of times brighter than it is right now, is less than #0. 4# is greater than. From the surface of Mars, if anyone or anything were watching, the Sun would fill half the sky. A bloated, pulsating red monster, its surface not smooth but churning with convective cells the size of planetary orbits, each one a hurricane of plasma, large enough to swallow Jupiter. The Sun will no longer look like a star. It will look like a wound in the sky. And as it swells, it bleeds. The red giant Sun will lose mass at a staggering rate through violent stellar winds. Material from the outer layers will be flung into space in gusts that strip away the Sun's substance year by year. By the time the expansion is complete, the Sun will have shed between 20 and 30% of its total mass. That is a colossal amount. During the peak of the red giant phase, the Sun will be ejecting material at a rate equivalent to roughly 8% of Earth's mass every single year. This mass loss has consequences far beyond the Sun itself. As the Sun loses mass, its gravitational grip on the solar system weakens. The planets, those that survive, will drift outward into wider orbits. The entire architecture of the solar system will shift. Distances that have been stable for billions of years will change. And for the inner planets, the change will come far too late. In 2024, Kemming Jung and colleagues published a landmark discovery in Nature Astronomy. They found an Earth-mass planet orbiting a white dwarf star at roughly 2 astronomical units, the first evidence that a rocky planet can survive its star's red giant phase. The system is called KMT 2020 BLG 0414, and it sits roughly 4,300 light-years from us. The discovery was groundbreaking because it suggested that survival is at least possible. But Jung was careful to note that the question of Earth's fate remains unresolved. We do not currently have a consensus whether Earth could avoid being engulfed by the red giant Sun in 6 billion years. The competing forces are brutally simple. On one side, the Sun's mass loss weakens gravity and pushes Earth's orbit outward. On the other side, tidal drag from the swollen Sun's enormous envelope tries to pull Earth inward, spiraling it toward destruction. Which force wins depends on variables we cannot yet precisely model. The timing of the expansion, the rate of mass loss, the exact dynamics of tidal friction between a planet and an atmosphere that extends for millions of miles. What we do know is that the Sun has become a monster, a bloated red giant, 256 times its former size, reaching outward with superheated plasma, and directly in its path sit Mercury, Venus, and a scorched rock that was once our home. Chapter 3. Mercury, Venus, and Earth get eaten. Mercury goes first. It never had a chance. The smallest planet in the solar system, already scorched by its proximity to the Sun, is swallowed by the expanding red giant envelope long before the Sun reaches its maximum size. But Mercury does not simply vanish in a flash of light. As the Sun's outer atmosphere engulfs it, tidal forces begin to spiral the planet inward. The expanding stellar envelope creates drag, friction against a planet moving at orbital velocity through a medium of superheated gas. Mercury slows, it spirals closer, and it dissolves. Not shatters, not explodes, dissolves. The temperatures inside the red giant's envelope range from thousands to tens of thousands of degrees. Mercury's rocky surface melts, its iron core, once the densest in the solar system relative to the planet's size, softens and disperses. The material that was Mercury mixes into the Sun's outer layers, becoming indistinguishable from the stellar plasma around it. Billions of years of planetary history, the cratered surface that recorded the solar system's violent youth, the magnetic field generated by a core proportionally larger than any other planet's, all of it gone, absorbed into the dying star as if it never existed. Venus follows. Already a hellscape of crushing atmosphere and surface temperatures hot enough to melt lead, Venus encounters the expanding Sun and meets the same fate. Tidal drag spirals it inward. The atmosphere is stripped, the surface melts, the planet ceases to exist as a distinct object. It is simply consumed, mixed into the stellar envelope, like a grain of salt dropped into an ocean. Two planets erased, no trace, no remnant, just atoms scattered through the dying body of the star that created them. And then there is Earth. Earth sits right on the boundary, right at the edge of survival and annihilation, and the scientific community genuinely does not know which side we fall on. The models disagree, and they disagree for good reason, because the physics involved is extraordinarily complex, is less than #0. 4# is greater than. Here is the dilemma. As the Sun loses mass through its violent stellar winds, its gravitational hold on Earth weakens. A lighter Sun means a weaker pull, and a weaker pull means Earth's orbit naturally expands outward. By some calculations, Earth could migrate to roughly 1.5 to 2 astronomical units by the time the Sun reaches peak expansion, potentially placing it just beyond the reach of the swollen stellar surface. But tidal friction works in the opposite direction. The Sun's bloated envelope extends for hundreds of millions of miles. If Earth passes through even the outermost wisps of that envelope, drag forces will slow its orbital velocity. A slower orbit means the planet spirals inward, and inward in this context means into the Sun. The question is whether Earth's outward migration from mass loss outpaces the inward drag from tidal friction. The answer depends on timing, on how quickly the Sun expands versus how quickly it loses mass, on the precise density of the outermost layers of the envelope at Earth's orbital distance. The KMT 2020 BLG 0414 discovery in 2024 offered a tantalizing clue. Here was a rocky planet with roughly Earth's mass, orbiting a white dwarf at about 2 astronomical units. That is approximately the distance Earth would need to reach to survive. The planet had made it through its star's red giant phase. It was battered, stripped of any atmosphere, a dead rock in orbit around a stellar corpse. But it was there. It existed. Survival was possible. Carl Mellis, an astrophysicist at the University of California, San Diego, captured the stakes perfectly. Our solar system is relatively boring and stable today. But when the Sun begins to die, all bets are off. There are many studies of what will happen dynamically, and it is not pretty. So let us imagine both scenarios. If Earth escapes, it will be a Pyrrhic victory. By the time the red giant phase arrives, Earth has already been dead for billions of years. The oceans boiled away long ago. The atmosphere was stripped. The surface is a scorched, irradiated wasteland with no magnetic field, no water, no life of any kind. Earth, at 2 astronomical units from a red giant sun, is not a saved planet. It is an orbiting tombstone, a charred husk circling a dying star, carrying the fossilized memory of a world that once harbored life, now as barren and silent as any asteroid. And if Earth does not escape, if tidal friction wins, Earth enters the Sun's outer envelope at roughly its orbital velocity, 30 kilometers per second, through a medium of hot, diffuse plasma. The first thing to go is whatever remains of the atmosphere, stripped instantly by the superheated gas, then the surface. Atmospheric drag generates friction, and friction generates heat. The crust begins to ablate, melting and peeling away like paint under a blowtorch. But Earth does not burn up instantly. This is not a meteor flashing through our atmosphere. Earth is massive, dense. It takes time. According to models by Avi Loeb and others, Earth could take thousands of years to fully dissolve inside the Sun's envelope. Thousands of years of spiraling inward through layers of progressively hotter and denser plasma, each orbit tighter than the last, each pass stripping more material from the surface. The mantle goes next. The silicate rock that makes up the bulk of Earth's interior, 4.5 billion years of geological history, the layers that recorded every earthquake, every volcanic eruption, every movement of every tectonic plate, melted and dispersed into the stellar atmosphere. And the last thing to go, the very last piece of Earth, will be the iron core. Dense, heavy, the innermost part of the planet. It will be the final remnant, a small, glowing sphere of molten iron spiraling through the deepest layers of the Sun's dying body. Everything, every mountain, every ocean bed, every fossil, every city ever built, every footprint, every fingerprint, every word ever written, all of it becomes part of the Sun's dying breath, mixed into the stellar material that will eventually be expelled into space. The atoms that were once Earth will drift through the interstellar medium for billions of years, and some of them, eventually, will end up inside a new star, a new planet, perhaps even a new living thing. But that is a story for later. Right now, the inner solar system is gone. Mercury, Venus, and possibly Earth have been consumed or scorched beyond recognition. Mars has been irradiated and pushed into a wider orbit. The asteroid belt is disrupted. The inner solar system, the part we call home, is a graveyard. But something extraordinary is happening billions of kilometers further out. Something that no one expected. Because while Earth burns, the frozen moons of Jupiter are coming back to life. Chapter 4, Life After Earth, the Thawing of Europa. While the inner solar system is consumed by the expanding red giant, something almost miraculous is happening in the outer solar system. The habitable zone, that narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface, is migrating outward, and it is heading straight for Jupiter. For billions of years, Jupiter's system has been a frozen wasteland as far as surface habitability is concerned. Jupiter itself is a gas giant with no solid surface, wrapped in a crushing atmosphere of hydrogen and helium. Its moons are encased in ice, bombarded by radiation from Jupiter's intense magnetic field, and locked in perpetual cold. Europa, one of the 4 large Galilean moons, has a surface temperature of roughly -160 degrees Celsius. Its ice shell is estimated to be anywhere from 15 to 25 kilometers thick. Beneath that shell, most planetary scientists believe, lies a global ocean of liquid water kept warm by tidal heating from Jupiter's gravitational pull. But the surface is a frozen desert, until the Sun dies. In May 2025, a team of researchers at Cornell University's Carl Sagan Institute published a breakthrough paper In the monthly notices of the Royal Astronomical Society, Elijah Mullins, Brittany Schmidt, Lisa Kaltenegger, and Nicole Lewis modeled what would happen to Europa as the Sun swelled into a red giant and the habitable zone swept outward past Jupiter's orbit. The title of their paper captured the poetry of it perfectly: Life After Death, Europa in the Evolving Habitable Zone of a Red Sun. What they found was remarkable. As the Sun's luminosity increases during the red giant branch, the installation, the amount of stellar energy hitting Europa, rises dramatically. Europa's thick ice shell begins to sublimate, transitioning directly from solid ice to water vapor under the increased radiation. But the process is not uniform. Jupiter's own brightness increases as it reflects more light from the swollen Sun, and this reflected light hits Europa's sub-Jovian hemisphere, the face that always points toward Jupiter, hardest. That hemisphere sublimates first. As the Sun continues to brighten, the anti-Jovian hemisphere follows. Europa develops an atmosphere, not a thick one, a tenuous envelope of water vapor, thin by Earth standards but stable. And this is the critical finding of the paper. That atmosphere is stable against atmospheric loss for at least 200 million years. 200 million years of a water vapor atmosphere on a moon that for billions of years had nothing but vacuum above its ice. To put 200 million years in perspective, that is comparable to the entire Mesozoic era on Earth, the age of dinosaurs. The period from the first dinosaurs to the last, from the earliest mammals to the extinction event that cleared the way for us. All of that happened in roughly 180 million years. Europa would have a habitable window of similar duration. And Europa is not starting from zero, it already has the building blocks for life. A global subsurface ocean containing more liquid water than all of Earth's oceans combined. Energy from tidal heating driven by Jupiter's gravity. Complex chemistry at the boundary between the ocean floor and the rocky interior. Organic molecules detected on the surface by observations from the James Webb Space Telescope and the Hubble Space Telescope. Salt compounds that suggest ocean water is reaching the surface through cracks in the ice. The Sun's death does not just melt Europa's ice, it exposes the subsurface ocean. For the first time in the Moon's history, the water beneath the shell would have direct contact with an atmosphere and with starlight. The conditions that scientists have long speculated could support life in Europa's hidden ocean would suddenly exist on the surface, under a red sky, warmed by a dying star. Kemming Jung captured the implications in 2024 when discussing the broader consequences of the Sun's red giant phase. As the Sun becomes a red giant, the habitable zone will move to around Jupiter and Saturn's orbit, and many of these moons will become ocean planets, not frozen moons hiding their water beneath kilometers of ice. Ocean planets, worlds with liquid water on their surfaces, in the habitable zone of a star for hundreds of millions of years. And Europa is not the only candidate. Saturn's moon Titan, the only moon in the solar system with a thick atmosphere, could undergo its own transformation. Under current conditions, Titan's atmosphere is a haze-choked soup of nitrogen and methane, far too cold for liquid water. But research suggests that under the lower ultraviolet flux of a red giant, Titan's haze production would drop significantly. The atmosphere would clear, and with the increased warmth, Titan could develop liquid water, ammonia, oceans on its surface. A different kind of habitability. Ammonia lowers the freezing point of water and creates a solvent that some astrobiologists believe could support exotic biochemistry. Saturn's moon Enceladus, already known to be venting plumes of water vapor and organic molecules from its subsurface ocean through cracks in its south polar ice, would experience similar thawing. The geysers that Cassini observed erupting from Enceladus could become permanent features of a moon transitioning from frozen to temperate. Even moons and dwarf planets in the Kuiper belt, objects like Pluto and Eris, that are currently locked in deep freeze at the outermost edges of the solar system, would experience significant warming. Their surface ices, composed of nitrogen, methane, and water, would begin to sublimate and potentially create temporary atmospheres. The delayed gratification habitable zone, as one researcher called it, would extend far beyond Jupiter, creating a belt of newly warmed worlds stretching across the outer solar system. The Mullins team captured the philosophical weight of their discovery in a single sentence. It is possible that in a fiery, dramatic end to one part of the system, life could find new beginnings. There is something almost unbearably poignant about this. Earth dies, but Europa wakes up. The planet that harbored life for 4 billion years is consumed by the sun, and simultaneously, a frozen moon that has waited in silence for just as long finally gets its chance. The death of one world seeds the possibility of another. The habitable zone does not disappear when the sun swells. It moves, and the question of whether life can exist in our solar system does not end with Earth. It migrates outward to moons we are only now beginning to understand. But Europa's renaissance is fleeting. The sun is not done dying yet. What comes next is one of the most violent events in stellar physics. An explosion inside the sun so powerful it briefly rivals the energy output of the entire Milky Way galaxy. And the strangest part? From the outside, you would never know it happened. Chapter 5. The Helium Flash, a bomb inside a dying star. Deep inside the red giant, beneath the bloated envelope of cooling plasma that now stretches across the inner solar system, the sun's core is in trouble. The hydrogen shell burning that inflated the star has been dumping helium ash onto the core for millions of years. The core is now a dense ball of helium, compressed to extraordinary densities by the weight of everything above it. And it is in a state of matter so bizarre that it defies everyday intuition. The core is degenerate. That word, degenerate, has a specific meaning in physics. At the densities inside the sun's collapsing core, the electrons are packed so tightly that a quantum mechanical principle called the Pauli exclusion principle takes over. This principle states that no two electrons can occupy the same quantum state. When matter is compressed to the point where electrons cannot be squeezed any closer without violating this rule, the electrons push back, not with thermal energy, not with heat, but with pure quantum mechanical pressure. This is called electron degeneracy pressure, and it is what holds the sun's core up against the crushing force of gravity. Here is why this matters. In normal matter, when you add heat, the material expands. This is a thermostat, a natural feedback mechanism. If the core of a normal star gets too hot, it expands, the density drops, the fusion rate slows, and the temperature comes back down. It is self-regulating. Degenerate matter does not work this way. When you add heat to degenerate matter, it does not expand. The electron degeneracy pressure is independent of temperature. You can heat degenerate matter to 100 million degrees and it will just sit there, getting hotter and hotter with no safety valve, no thermostat, no feedback. The temperature rises and nothing stops it. Now, here is what is happening inside the sun. The helium core, supported by degeneracy pressure and not by thermal pressure, is being heated by the hydrogen shell burning above it. The temperature climbs. 50 million Kelvin, 60 million, 80 million. The helium sits there, inert, getting hotter, with no mechanism to relieve the pressure. And then, at approximately 100 million Kelvin, something ignites. Helium fusion begins. Through a process called the triple alpha process, 3 helium nuclei, known as alpha particles, collide and fuse to form a single carbon-12 nucleus. This reaction requires extraordinary temperatures because the intermediate step, the formation of beryllium-8 from 2 helium-4 nuclei, produces an isotope that is violently unstable. Beryllium-8 decays in roughly 0.07 femtoseconds. For the triple alpha process to work, a third helium nucleus must collide with the beryllium-8 before it falls apart. At 100 million Kelvin, this begins to happen. And because the core is degenerate, There is no feedback. The temperature spikes. The fusion rate skyrockets. More fusion means more heat. More heat means a faster fusion rate. More fusion means even more heat. A thermonuclear runaway, an uncontrolled chain reaction inside the core of a dying star. This is the helium flash. For a few minutes, the helium flash produces energy at a rate comparable to the luminosity of the entire Milky Way galaxy. Billions of times the Sun's normal energy output, concentrated in a core no larger than the Earth, for a brief, furious burst. It is one of the most energetic events in stellar physics. And here is the strange part. From the outside, nothing happens. The helium flash occurs deep within the Sun's interior, buried under an envelope of gas hundreds of millions of kilometers thick. The energy released by the flash is entirely absorbed by the overlying layers of the star. It never reaches the surface as visible light. If you were watching the Sun from a safe distance during the helium flash, you would see a quiet red giant, slowly pulsating, utterly unremarkable. You would have no idea that a thermonuclear detonation rivaling the output of an entire galaxy had just occurred in its core. But the flash has consequences. The enormous burst of energy violently breaks the core out of its degenerate state. The core expands, the temperature drops slightly, and for the first time in millions of years, the core stabilizes. Helium fusion continues, but now in a controlled, steady manner. The Sun contracts back down, shrinking from its bloated red giant form to a smaller, hotter configuration called the horizontal branch. The Sun has entered its second life. Helium fusion in the core produces carbon and oxygen, the two elements that will eventually make up the Sun's final corpse. This phase lasts roughly 100 million years. A brief encore compared to the 10 billion years of hydrogen burning on the main sequence. And helium is a less efficient fuel. It burns faster and produces less energy per unit of mass. The clock is ticking. When the helium in the core is exhausted, the cycle repeats. But this time, it is worse. The carbon-oxygen core, now inert, contracts and heats. Helium fusion ignites in a shell around the core, just as hydrogen burning occurred in a shell before. But now there are two shells, an inner shell burning helium and an outer shell burning hydrogen, layered like an onion of nuclear fire. This configuration is catastrophically unstable. The Sun enters the asymptotic giant branch, and it begins to pulsate. Thermal pulses, sometimes called cosmic hiccups, rip through the star at irregular intervals. Each pulse dumps energy into the outer layers, causing the star to swell and then partially contract. Each expansion ejects more material into space. The Sun is shedding its outer layers in violent bursts called superwinds, blowing material outward at speeds that strip the star bare layer by layer. Each pulse is more violent than the last. Each one tears away more of the Sun's substance. The star is literally coming apart from the inside out, its internal structure oscillating between states of fusion and collapse, each cycle pushing more material into space and exposing deeper, hotter layers. The helium has run out. The carbon-oxygen core sits inert, unable to ignite further fusion. The Sun is not massive enough to compress carbon to the temperatures needed for the next stage of nuclear burning. That requires a star at least 8 times the mass of the Sun. Our star has reached its limit. The nuclear engine has burned its last fuel, and now the Sun does something no one would expect from a dying star. It creates one of the most beautiful objects in the entire universe. Chapter 6: The Most Beautiful Corpse in the Galaxy. The Sun is tearing itself apart. On the asymptotic giant branch, racked by thermal pulses and superwinds, the dying star ejects its outer layers into space in a series of violent bursts, not all at once. In waves, each pulse pushes another shell of gas outward, and over thousands of years, up to half of the Sun's total mass is blown into the void. This is not destruction in the way we usually think of it. This is a shedding. a star removing its own skin, and what lies beneath is something extraordinary. As the outer layers peel away, they reveal the sun's naked core, a tiny, blazing hot remnant, shrinking down to roughly the size of Earth but still containing more than half the sun's original mass. This exposed core is staggeringly hot, far hotter than the sun's surface ever was during its main sequence life. And as the layers above it thin and become transparent, the core begins to flood the surrounding space with radiation. For a long time, there was genuine scientific debate about whether the sun would produce a visible planetary nebula. The question hinged on timing. The ejected gas shell expands outward and dissipates. If the core heats up too slowly, the shell will have dispersed into the interstellar medium before it can be illuminated. The sun would die in darkness, its last exhalation fading unseen. In 2018, Albert Zylstra and colleagues at the University of Manchester settled the debate. Their research, published in Nature Astronomy, showed that the sun's exposed core heats up 3 times faster than previous models had predicted. This faster heating means the core reaches the temperatures necessary to ionize the surrounding gas, while the ejected shell is still dense enough to glow. The sun will produce a planetary nebula. It will be faint by cosmic standards, near the lower limit of visibility, but it will be there. The process works like this. As the core's temperature rises above 100,000 Kelvin, it begins to emit intense ultraviolet and X-ray radiation. This radiation strikes the expanding shell of gas that the sun ejected during its death throes. The energy from the radiation excites the atoms in the gas, stripping electrons from hydrogen and oxygen, ionizing the cloud. When those electrons recombine with the ions, they emit light at specific wavelengths. Hydrogen glows red. Oxygen glows a ghostly blue-green. The timing of this illumination is precise. Hydrogen begins to glow first, roughly 5,000 years after the core is fully exposed. Oxygen follows about 7,500 years later, adding its cooler, eerier light to the mix. The result is a planetary nebula, a shell of glowing gas surrounding a tiny, intensely bright central star. Zylstra captured the aesthetic significance beautifully. These planetary nebulae are the prettiest objects in the sky, and even though the sun will only become a faint one, it will be visible from neighboring galaxies. The nebula will be visible from millions of light years away. Astronomers in Andromeda, if any exist, could look toward our galaxy and see the sun's death. A tiny point of glowing gas, ephemeral and delicate, marking the end of a star that burned for 10 billion years. And the shapes these nebulae take are some of the most astonishing structures in the cosmos. Planetary nebulae display an extraordinary range of forms: butterfly wings, hourglasses, spirals, rings within rings, pinwheels of light. The Cat's Eye Nebula, one of the most studied planetary nebulae, shows at least 11 concentric shells surrounding its central star, each one the record of a separate ejection event. The Helix Nebula looks like a giant eye staring across space. The Red Spider Nebula extends filaments of gas that reach trillions of miles. The origin of these complex shapes is still not fully understood. If a star simply ejected a spherical shell of gas, you would expect a spherical nebula, but almost no planetary nebulae are spherical. The asymmetries are thought to arise from interactions between the ejected material and the star's magnetic field, the rotation of the dying star, and in many cases the gravitational influence of unseen companion objects. Binary partners, planets, or even brown dwarfs can shape the outflow, deflecting material into jets and rings that produce the wild geometries we observe. The Sun's planetary nebula will not be the most spectacular in the galaxy. It lacks the mass for truly dramatic structures, but it will exist. A delicate shell of red and green light, expanding outward at tens of kilometers per second, thinning as it goes, a ghost of the star it once was. And it will not last long. Planetary nebulae are among the most short-lived structures in the universe. They persist for roughly 10 to 30,000 years before the gas has expanded and thinned to the point where it can no longer glow. 30,000 years. The Sun burned for 10 billion years, and its final visible monument will last for less than 30,000. A blink, a flash, a single breath in a life measured in eons. But in that brief window, the Sun gives something back. The material in the planetary nebula is not just hydrogen and helium. It contains elements forged in the Sun's core over billions of years. Carbon, produced by the triple alpha process during helium burning. Nitrogen, created through the carbon-nitrogen-oxygen cycle during hydrogen shell burning. Oxygen, the byproduct of helium fusion in the later stages. These elements are now being dispersed into interstellar space, seeded into the gas and dust between the stars. And this is where the story of the Sun's death becomes the story of something else entirely. Because these atoms, these carbon and nitrogen and oxygen atoms that the Sun forged in its core and exhaled in its dying breath, will not disappear. They will drift through the galaxy for millions of years. They will accumulate in vast molecular clouds, and eventually, gravity will pull those clouds together. New stars will form. New planets will coalesce from the enriched dust. And on some of those planets, the conditions for life may exist again. Every carbon atom in your body was once inside a star. Every oxygen atom you breathe was forged in a stellar core. The Sun will return the favor. Its atoms will become part of new worlds. The Sun's death is not an ending. It is a contribution, a deposit into the cosmic account from which future solar systems will draw. But that dispersal is in the future. Right now, the nebula is fading. The gas is thinning. The light is dimming. And all that remains is the Sun's exposed heart. A strange, impossibly dense object, the size of Earth with half the mass of a star. And over the next trillion years, something even stranger will happen to it. Chapter 7. The White Dwarf, a star the size of Earth. The planetary nebula fades. The gas disperses into the interstellar medium, and what is left behind is one of the strangest objects in the universe. The Sun's core, now stripped bare, has contracted to roughly the size of Earth, but it still contains about half the mass of the original star. Imagine taking half the Sun and compressing it into a sphere no larger than our planet. The result is a white dwarf. The density is almost impossible to comprehend. A single teaspoon of white dwarf material would weigh somewhere between 5 and 15 tons. The core density reaches approximately 10 million grams per cubic centimeter. That is 1 million times denser than water, denser than anything you have ever encountered, denser than anything that exists naturally on Earth by a factor of millions. If you could somehow place a sugar cube of this material on the ground, it would weigh as much as a large truck. And yet this object is not held up by any ongoing process of energy generation. There is no nuclear fusion inside a white dwarf. The hydrogen is gone. The helium is gone. What remains is a core of carbon and oxygen, the ash of billions of years of nuclear burning, compressed beyond anything classical physics would allow. The white dwarf is supported entirely by electron degeneracy pressure, the same quantum mechanical force that held up the helium core before the helium flash. Electrons, packed so tightly that the Pauli exclusion principle prevents them from being compressed further, push back against gravity. And that is all. That is the only thing standing between this Earth-sized object and total gravitational collapse. The surface temperature of a newborn white dwarf is extraordinary, over 100,000 Kelvin, hot enough to glow blue-white, hot enough to emit intense ultraviolet radiation. Hot enough that if you could see it from close range, it would be painfully, blindingly bright, despite being no larger than a planet. But this brightness is borrowed time. The white dwarf has no energy source. It is cooling, radiating its stored thermal energy into space. And it will continue doing this for a very, very long time. There is a ceiling on how massive a white dwarf can be. In 1930, the Indian astrophysicist Subramanian Chandrasekhar, at the age of 19, calculated the upper limit during a sea voyage from India to England. The limit is 1.4 solar masses, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure is not strong enough to resist gravity. The star would collapse further, becoming either a neutron star, where protons and electrons are crushed together into neutrons, or a black hole. The Sun's white dwarf remnant will be safely below this limit, at roughly 0.5 to 0.6 solar masses. It will never become a neutron star. It will never become a black hole. It will never explode as a supernova. This is the Sun's final form, a quiet, dense, slowly cooling crystalline remnant, the end of the road for a star that was never quite massive enough for a more dramatic death. Now look at the solar system. What does it look like around this tiny, brilliant point of light? Mercury and Venus are gone, consumed during the red giant phase. Earth may be gone, or it may survive as a charred, atmosphere-stripped dead rock, orbiting at roughly 2 astronomical units, a mute witness to its own star's death. Mars has been pushed outward, irradiated by the intense pre-white dwarf winds that blew at over 2,000 kilometers per second during the transition. The asteroid belt has been disrupted, its delicate gravitational choreography thrown into chaos by the Sun's mass loss. The outer planets survive. Jupiter, Saturn, Uranus, Neptune are all still there, but their orbits have expanded significantly. When the Sun lost half its mass, its gravitational grip weakened. The planets drifted outward, settling into new, wider orbits around a star that is now a tiny fraction of its former self. The Kuiper belt has been partially scattered. The Oort cloud, the vast sphere of icy bodies that extends to the outermost edges of the Sun's gravitational influence, has been disrupted by the mass loss and by close encounters with passing stars over billions of years. The solar system is a ghost town, cold, dark, vast, and mostly empty. Where the Sun once blazed as a warm yellow star dominating the sky, there is now a tiny point of blue-white light. Bright, yes, but concentrated into a dot no bigger than a planet. From the surface of any surviving world, the Sun would look like an intensely bright star, not a disk. You would not feel its warmth, you would see its light. But the era of a sun that could heat a planet and sustain life is over. The hot pre-white dwarf winds that blew during the transition between red giant and white dwarf have stripped the outer atmospheres of the gas giants. Jupiter and Saturn, those magnificent banded worlds of swirling clouds and violent storms, have been diminished. Their upper atmospheres, blasted by winds carrying the Sun's ejected material at thousands of kilometers per second, have been partially eroded. They are still gas giants, they are still massive, but they are wounded, changed, carrying the scars of their star's death. Europa's brief renaissance is ending, or has ended by now. The habitable window of 200 million years was generous by cosmic standards, but fleeting by geological ones. As the Sun transitions from red giant to white dwarf, its luminosity drops precipitously. The habitable zone contracts. The warmth that melted Europa's ice shell and gave it an atmosphere retreats inward, past Jupiter, past Mars, past Earth's empty orbit, and eventually to a zone so close to the white dwarf that no surviving world occupies it. Europa freezes again. The water vapor atmosphere condenses and falls as snow. The ice returns, the window closes, and the white dwarf sits in silence, radiating the last of its stored heat into an empty solar system, a single brilliant point of light in an ocean of darkness. But inside this tiny star, something astonishing is happening. On a timescale no human mind can truly comprehend. The Sun is turning into a diamond. Chapter 8. The Cosmic Diamond. Crystallization of a Dead Star. The white dwarf has no engine, no fusion reactor in its core, no source of new energy. It is simply cooling, radiating the thermal energy stored from billions of years of nuclear burning into the void, degree by degree, over timescales that dwarf everything we have discussed so far. The cooling is agonizingly slow. A white dwarf, born at over 100,000 Kelvin, does not reach room temperature in a few million years. It does not even get close. The process is so drawn out that white dwarfs formed in the earliest epochs of our universe, stars that died over 10 billion years ago, are still warm, still glowing, still radiating at surface temperatures of roughly 4,000 degrees Celsius. After more than 10 billion years of cooling, they are still hotter than the surface of a red dwarf star. In 2019, data from the European Space Agency's Gaia satellite revealed something unexpected in the population of white dwarfs within 100 parsecs of the Sun. There was a pile-up, a clustering of white dwarfs at a specific luminosity and temperature that should not have been there if the stars were cooling smoothly. Something was slowing them down. Something was releasing energy inside these dead stars, delaying their cooling in a way that the standard models had predicted but never directly observed. The answer was crystallization. As a white dwarf cools, its interior undergoes a phase transition. The carbon and oxygen ions, which exist as a superheated fluid at the core's birth, begin to slow down. Their thermal energy drops. And at a critical temperature, they begin to form bonds. They arrange themselves into a regular, repeating structure, a crystal lattice. The interior of the white dwarf begins to solidify, and this solidification releases latent heat, the same way water releases heat when it freezes into ice. That latent heat is enough to delay the cooling process by roughly 1 billion years. 1 billion years of extra warmth from the simple act of freezing. The 2019 Gaia observations confirmed this prediction. The pile-up in the cooling sequence was real, and it was caused by crystallization. White dwarfs were not just cooling, they were freezing solid from the inside out, and the freezing was keeping them warm. But in 2024, the story got stranger, much stranger. Antoine Bedard at the University of Warwick, Simon Bluin at the University of Victoria, and Sihao Cheng at the Institute for Advanced Study in Princeton published a paper in Nature that revealed a completely new phenomenon. They had been studying a population of white dwarfs that were not just pausing in their cooling. They were maintaining a constant luminosity for a duration comparable with the age of the universe. Billions of years of steady brightness from stars that had no energy source. Something was generating enormous amounts of energy inside these dead stars, far more than simple latent heat could account for. What they discovered was a process called distillation. In certain white dwarfs, particularly those formed from the merger of two smaller stars, the core composition is slightly different from standard white dwarfs. When these cores begin to crystallize, the solid crystals that form are depleted of heavier elements. They are lighter than the surrounding liquid, and because they are lighter, they float. Imagine ice forming at the bottom of a glass of water and rising to the surface. That is roughly what is happening inside these white dwarfs, except the ice is crystallized carbon-oxygen and the water is a superheated quantum fluid of degenerate matter. The buoyant crystals float upward through the liquid interior. As they rise, they displace heavier liquid downward, and that downward displacement of heavier material releases gravitational energy. The heavier stuff falls, the lighter stuff rises, and the difference in gravitational potential is converted into heat. This gravitational energy release is enormous, enough to halt the cooling of the white dwarf for billions of additional years. Bedard captured the significance of the discovery. This is the first time this transport mechanism has been observed in any type of star, which is exciting. It is not every day we uncover a whole new astrophysical phenomenon. The implications ripple outward. White dwarfs are routinely used as cosmic clocks. Because they cool at a predictable rate, astronomers use their temperature to estimate their age. A cooler white dwarf is assumed to be older. But if some white dwarfs are maintained at constant brightness for billions of years by floating crystals, then some stars that appear young based on their temperature may actually be billions of years older than anyone thought. The cosmic clock needs recalibrating. There is even a specific star that serves as a case study, HD 190412c. A white dwarf, approximately 104 light-years from Earth, is part of a quadruple star system. Because the ages of the companion stars can be independently determined, researchers were able to pin down the white dwarf's age with unusual precision. The results showed that its core is roughly 65% crystallized. It is the first confirmed crystallizing white dwarf with a known age, and it provides a direct testbed for the new crystallization models. Now, extrapolate this forward, way forward. Over trillions of years, the crystallization process continues. Layer by layer, the liquid interior solidifies. The crystal lattice grows outward from the center, locking carbon and oxygen ions into a rigid structure. The white dwarf transitions from a liquid core with a solid shell to a mostly solid body to, eventually, a completely crystallized object. And what is a solid, crystalline sphere of carbon? It is a diamond. Not metaphorically, not poetically, structurally. Carbon atoms, arranged in a crystal lattice, is the definition of diamond. The Sun's white dwarf remnant, over timescales measured in the trillions and eventually quadrillions of years, will solidify into a planet-sized diamond. A cosmic jewel floating in the void, containing half the mass of the original star, locked in a crystalline embrace that will last for an eternity, that makes the current age of the universe look like a rounding error. Full crystallization into a cosmic diamond would take approximately 1 quadrillion years, that is 10 to the 15th power, a 1 followed by 15 zeros. The universe is currently 13.8 billion years old. A quadrillion years is roughly 70,000 times the current age of the universe. No white dwarf anywhere has yet fully crystallized. The process has barely begun, even in the oldest white dwarfs that exist. But it is underway. We can see it happening in stars we observe right now. A diamond the size of Earth, floating in the void, slowly going dark. But even this is not the end. Because what happens when the diamond finally goes completely cold opens up one of the strangest chapters in the story of the universe. Chapter 9. The Black Dwarf. A star that does not exist yet. There is a type of object predicted by physics that has never been observed, not because it is rare, not because it is far away, because the universe is not old enough for one to exist yet. A black dwarf is the final evolutionary stage of a white dwarf star. When a white dwarf has radiated away every last joule of its residual thermal energy, when its surface temperature has dropped to match the temperature of the cosmic background radiation, when it emits no light, no heat, no radiation of any kind, it becomes a black dwarf, a cold, dark, crystallized husk, invisible to any telescope, detectable only through its gravitational influence on nearby objects, a ghost in the void. The time required for this to happen is staggering. At minimum, 1 quadrillion years, possibly much longer, given the newly discovered crystallization delays from buoyant crystals that can extend the cooling process by billions of additional years. The universe, at 13.8 billion years old, has completed roughly 100,000th of 1% of the time needed for the first black dwarf to form. We are not close. We are not even in the same order of magnitude as close. Black dwarfs are entirely theoretical. They are a prediction, a logical endpoint extrapolated from the physics of white dwarf cooling. No one has seen one. No one will see one for timescales that exceed not just human comprehension, but the comprehension of any temporal framework we possess. A quadrillion years is a number we can write but cannot feel. It is 70,000 times the current age of the cosmos. If the entire history of the universe from the Big Bang to this moment were compressed into a single second, a quadrillion years would be roughly 20 hours. We are 1 second into a day. Now imagine the universe when black dwarfs finally form. It will be unrecognizable. Star formation will have ceased trillions of years prior. The raw material, the vast molecular clouds of hydrogen and helium that collapse under gravity to birth new stars, will have been used up. The last red dwarf stars, those small, miserly furnaces that burn their hydrogen so slowly they can persist for trillions of years, will have finally gutted out. The galaxies, as we know them, will have dispersed. Gravitational interactions over trillions of years will have ejected most stars from their galaxies. The remaining ones will have spiraled inward and been consumed by the supermassive black holes at galactic centers. The universe will be dominated by remnants. Black holes slowly evaporating through Hawking radiation, neutron stars cooling toward invisibility, and white dwarfs, vast populations of them, scattered through the darkness, gradually approaching their own black dwarf fate. The cosmic microwave background radiation, the afterglow of the Big Bang that currently permeates all of space at a temperature of 2.7 Kelvin, will have cooled to almost absolute zero. The universe will be a vast, cold, nearly empty void dotted with invisible objects. The era of light, the time in which stars shine and galaxies blaze and the universe is illuminated, represents a vanishingly small fraction of the universe's total history. If the universe lasts for a quadrillion years, then the era during which any stars shine at all occupies perhaps the first 10 trillion years. Less than 1% of the total. We live in the bright opening credits of a very long, very dark film. But even in the darkness, not everything is quiet. In 2024, a team led by J.R. Fuentes published a paper in the astrophysical journal Letters that revealed something surprising about crystallizing white dwarfs. As the liquid interior of a white dwarf begins to solidify, the remaining liquid undergoes convection. Hot liquid rises, cool liquid sinks, and this convective motion, combined with the white dwarf's rotation and the electrical conductivity of its degenerate matter interior, generates powerful magnetic fields. Not weak magnetic fields, powerful ones, up to 1,000,000 times stronger than Earth's magnetic field. These magnetic white dwarfs are born from the crystallization process itself. Their magnetism, a byproduct of the same phase transition that is slowly turning them into crystals. The dynamo is short, lived in astronomical terms, lasting perhaps a few 100 million years. But during that time, the white dwarf is wrapped in invisible lines of force that reach out into the surrounding space. And here is the eerie implication. Even after the white dwarf has cooled into a black dwarf, the magnetic field may persist. Locked into the crystalline lattice of the solidified core, the remnant magnetism could endure long after the star has gone dark. Black dwarfs would be invisible to the eye. They would emit no light, but they would still be magnetic, invisible cosmic magnets floating through the void, their presence detectable only by the deflection of charged particles, or the subtle bending of electromagnetic radiation passing nearby. Magnetic ghosts. That is what they would be. The remnants of stars that once lit the sky, now dark and cold but still carrying within their crystalline bodies the frozen echo of a magnetic field generated during their last act of internal activity. A memory of motion locked into stillness. A whisper of energy in a universe of silence. The sun's black dwarf will be one of these ghosts. Cold, dark, dense, crystallized, magnetic. A diamond the size of Earth carrying half the mass of a star that once warmed a planet and gave rise to life. Now adrift in a universe so empty that the nearest other object may be trillions of miles away. Black dwarfs, cold, dark, seemingly dead. But physics has one more surprise. In the unimaginably distant future, a number so large it would fill a book just to write it out, these dead stars will do something no one expected. They will explode. Chapter 10. The Last Fireworks. Black Dwarf Supernovae. In the universe as it exists today, massive stars die in supernovae when nuclear fusion in their cores produces iron. Iron is the end of the line for stellar fusion. Every element lighter than iron releases energy when fused. Iron does not. When iron accumulates in the core of a massive star, the core can no longer support itself against gravity. It collapses in milliseconds. The resulting rebound and shockwave tear the star apart in an explosion that briefly outshines an entire galaxy. Stars like the Sun are far too small for this kind of death. They lack the mass, the gravitational pressure, the core temperature to fuse elements beyond carbon and oxygen. They become white dwarfs. They cool, they crystallize, they go dark. And according to every reasonable expectation, that should be the end of the story. But it is not. In 2020, Matt Kaplan, a theoretical physicist at Illinois State University, asked a question that no one had formally investigated before. What happens to black dwarfs over truly extreme timescales? Not billions of years, not trillions, but timescales so long that the number required to express them would fill most of a page if written out as a 1 followed by zeros. The answer involves a phenomenon called quantum tunneling. In normal stellar fusion, nuclei need enough kinetic energy to overcome the electrostatic repulsion between their positive charges. You need heat, you need speed. You need collisions violent enough to force protons close enough together for the strong nuclear force to take over and bind them. In a black dwarf at temperatures approaching absolute zero, there is no heat. There is no kinetic energy to speak of. Thermonuclear fusion is impossible. But quantum tunneling does not care about temperature. Quantum mechanics allows particles to spontaneously appear on the other side of an energy barrier they should not be able to cross. It is not about having enough energy. It is about probability. There is always a small, non-zero chance that two nuclei sitting next to each other in a crystal lattice will tunnel through the electrostatic barrier between them and fuse. The probability is absurdly low. You could wait 1,000,000 years and not see a single fusion reaction in a black dwarf. But it is not zero, and over sufficiently long timescales, not zero becomes inevitable. This is called pycnonuclear fusion. Fusion driven not by heat, but by quantum tunneling in the dense, cold lattice of a crystallized star. And what pycnonuclear fusion does, over timescales that beggar the imagination, is slowly convert the carbon and oxygen in a black dwarf into heavier and heavier elements, silicon, nickel, and eventually iron. Iron is the death knell. As iron accumulates in the core of a black dwarf, it absorbs electrons through a process called electron capture. Each captured electron is one less electron contributing to the degeneracy pressure that holds the star up. The Chandrasekhar limit, the maximum mass a white dwarf can support, depends on the number of electrons available. As electrons are consumed, the effective Chandrasekhar limit drops. And for the most massive black dwarfs, those between roughly 1.2 and 1.4 solar masses, the limit eventually drops below the star's actual mass. When that happens, gravity wins, the star collapses, and the collapse triggers a supernova, a black dwarf supernova, the last explosion the universe will ever see. Kaplan calculated the timescales. The first black dwarf supernovae will occur in approximately 10 to the 1100th power years from now. That number is almost impossible to convey. Kaplan described it this way. In years, it is like saying the word trillion almost 100 times. If you wrote it out, it would take up most of a page. The most massive black dwarfs explode first because their higher internal densities increase the tunneling rate. Progressively, less massive black dwarfs follow over even longer timescales. The last black dwarf supernova will occur at roughly 10 to the 32,000th power years from now, a number so large that writing it in standard notation would fill a chapter of a book. Kaplan estimated that approximately 1 billion trillion black dwarfs, about 1% of all stars in the observable universe, are massive enough to eventually meet this fate. If proton decay does not occur, and current physics offers no evidence that it does, then these supernovae are inevitable. They are the last interesting astrophysical events that will ever take place. But here is the part that makes this profoundly, almost unbearably lonely. By the time these explosions occur, the expansion of the universe driven by dark energy will have pulled every object so far apart that each black dwarf is completely alone. The observable universe for each individual black dwarf will have shrunk to effectively nothing. Light from the explosion will travel outward, but will never reach another object. There is nothing close enough. There is nothing anywhere. The explosion happens in absolute isolation, a silent detonation in absolute darkness, witnessed by nothing. Kaplan put it simply. It is hard to imagine anything coming after that. Black dwarf supernovae might be the last interesting thing to happen in the universe. They may be the last supernovae ever. And our Sun? Our Sun will not be among them. At roughly 0.5 to 0.6 solar masses, the Sun's black dwarf remnant is too light. It lacks the mass for pycnonuclear fusion to produce enough iron to trigger collapse. The Sun's final fate is not a supernova. It is not an explosion. It is not a blaze of glory. It is silence. Cold, permanent, absolute silence. A dark crystal floating through an empty universe. Forever. No light, no heat, no sound, no change. The Sun, which once burned at 15 million Kelvin in its core, which fused 600 million tons of hydrogen every second, which warmed a planet and gave rise to every living thing that ever existed on it, will end as a cold, dark, silent crystal, adrift in a void, so empty that the word empty itself fails to capture it. So the Sun's story ends in silence, a dark crystal floating through the void, forever. But what about us? What could humanity actually do to survive any of this? Is escape even possible? Chapter 11. Can we escape? Engineering, our survival. The Sun is going to kill everything on Earth within 1 billion years. It is going to swell into a red giant in 5 billion years and possibly consume the planet entirely. The white dwarf remnant will cool into a diamond and eventually go dark. The universe will end in silence. These are the facts. They are not negotiable. But humanity has one thing that no other species on this planet has ever possessed: the ability to see the future and the stubborn refusal to accept it. So let us talk about escape. Not science fiction, not fantasy. Real physics, real engineering concepts, real proposals from real scientists. Some of them are absurd by current standards. All of them are technically possible within the known laws of physics. And all of them operate on timescales so long that the difference between impossible and inevitable becomes surprisingly thin. The first and most immediate problem is the brightening Sun. Within 1 billion years, Earth's oceans will begin to evaporate. To survive, Earth needs to move outward, not by much, at first. Roughly 5% further from the Sun within the next 1 billion years. That translates to about 7.5 million kilometers. It sounds like a lot. It is a lot, but 1 billion years is also a lot of time. In 2025, Avi Loeb of Harvard University published a calculation exploring whether Earth's orbit could be expanded using asteroid gravity assists. The concept is elegant in its simplicity. You redirect a large asteroid, something from the asteroid belt or the Kuiper belt, to fly past Earth on a carefully calculated trajectory. As the asteroid passes, gravitational interaction transfers a tiny amount of orbital momentum from the asteroid to Earth. Earth's orbit expands by a minuscule amount. The asteroid, having lost momentum, falls into a tighter orbit. You then redirect it again, perhaps using a gravitational slingshot around Jupiter, and repeat. Each flyby transfers an almost imperceptibly small amount of energy, but over millions of years, with millions of flybys, the cumulative effect adds up. Earth creeps outward, the habitable zone expands. The oceans survive a little longer. It is not a quick fix. It is a project measured in geological time, but the physics works. To put the scale in perspective, Matteo Seriotti of the University of Glasgow calculated what it would take using current technology. Using Falcon Heavy rockets, you would need roughly 300 billion launches and 85% of Earth's mass as fuel. Absurd with today's technology, but instructive because it illustrates that the energy requirements, while vast, are finite. They are engineering problems, not physics problems. A civilization with millions of years of technological development might find them trivial. But moving Earth 5% solves only the first billion years. What about the red giant phase? To survive that, Earth would need to relocate to 50 to 70 astronomical units. Out past Neptune, out to the Kuiper belt. That is a fundamentally different challenge. You are not nudging an orbit, you are relocating a planet to the outer solar system. This is where the concepts become grander. A Shkadov thruster is a theoretical megastructure, a giant parabolic mirror positioned near the Sun. The mirror reflects the Sun's radiation in one direction, creating an asymmetric radiation pressure that generates thrust. The Sun itself becomes a rocket engine, slowly accelerating in one direction, dragging the entire solar system with it. The concept was proposed by Leonid Shkadov in 1987, and while it sounds fantastical, it violates no known law of physics. A more advanced concept is the Kaplan thruster, which would use the Sun's own material as fuel. By concentrating solar radiation to heat and eject solar wind material in a focused jet, you could generate thrust far more efficiently than the Shkadov mirror. The Kaplan thruster could theoretically move the Sun and its entire planetary system at a rate that would be meaningful over millions of years. A Dyson swarm, millions of solar collectors orbiting the Sun, could capture enough energy to power civilization through any transition. A full Dyson swarm around the current Sun could capture roughly 3.8 times 10 to the 26 watts of power. That is more energy than humanity currently uses by a factor of roughly 10 trillion. With that kind of energy budget, moving planets becomes a logistics problem, not a physics problem. But perhaps the most practical approach is not to move Earth at all. Perhaps the answer is to migrate. As the Sun swells and the habitable zone shifts outward, humanity, or whatever humanity has become after millions of years of evolution and technological development, could move to the outer solar system. Keming Jiang suggested exactly this. As the habitable zone moves to Jupiter and Saturn's orbit, the moons of those planets become viable homes. Europa, with its thawing ocean, Ganymede, the largest moon in the solar system, with its own magnetic field and subsurface water, Callisto, the most heavily cratered object in the solar system, with a possible subsurface ocean of its own, Enceladus, Saturn's tiny geyser moon, already venting water and organic molecules into space. Each of these worlds becomes a candidate for habitation during the red giant phase. And beyond the moons, there are the constructs. O'Neill cylinders, rotating, space habitats, first proposed by physicist Gerard O'Neill in 1974. Giant cylinders, kilometers long, spinning to generate artificial gravity on their interior surfaces. Filled with atmosphere, soil, water, vegetation, self-contained ecosystems floating in space. You do not need a planet. You need engineering. And a civilization with millions of years of development would have plenty of both. The final option is the most radical and arguably the most inevitable. Leave the solar system entirely. Become an interstellar civilization. The nearest star system, Alpha Centauri, is roughly 4.4 light-years away. With current technology, the journey would take tens of thousands of years. But with a civilization capable of building Dyson swarms and moving planets, interstellar travel is not a fantasy. It is a scheduling problem. Whether humanity escapes or not, the sun's death raises a question that goes deeper than survival. A question about the nature of death itself, written across the cosmos. Chapter 12: How Other Stars Die and Why Ours is Lucky. The sun's death is slow, drawn out over billions of years. A gentle swelling, a shedding of layers, a quiet cooling into crystalline darkness. By the standards of the cosmos, it is a peaceful death, almost dignified. And to understand why, you need to see what happens to stars that are not so lucky. Stars more massive than about 8 times the mass of the sun do not go gently. They detonate. These stars burn through their fuel at a furious rate, their enormous gravitational pressure driving fusion to temperatures and densities that the sun will never reach. Where the sun fuses hydrogen into helium and helium into carbon and oxygen before stopping, these massive stars keep going. Carbon fuses into neon, neon fuses into oxygen, oxygen fuses into silicon, and silicon fuses into iron. Each stage is shorter than the last. A massive star might burn hydrogen for 10 million years, helium for 1 million, carbon for 1,000, neon for a few years, oxygen for months, and silicon for a single day. One day of silicon burning, and the core is full of iron, and iron is where fusion stops. The moment the core fills with iron, the star is dead. It just does not know it yet. Within milliseconds, the iron core collapses. Electron degeneracy pressure fails. The core compresses from roughly the size of Earth to a sphere just 20 kilometers across. The infalling material rebounds off the suddenly incompressible core, sending a shockwave outward through the star's layers. Neutrinos, trillions upon trillions of them, flood outward, carrying away the gravitational binding energy of the collapse, and the star explodes. A core collapse supernova. In a few seconds, it releases more energy than the sun will emit in its entire 10 billion year lifetime. The explosion is visible across the universe. It can briefly outshine the entire galaxy it resides in. The shockwave ejects the star's outer layers at thousands of kilometers per second, seeding the surrounding space with heavy elements. Gold, platinum, uranium, all the elements heavier than iron, are forged in the supernova's fury and scattered into the interstellar medium. What remains depends on the mass. If the original star was between roughly 8 and 25 solar masses, the collapsed core survives as a neutron star, a sphere of pure neutrons, 20 kilometers across, with a density of 1 billion tons per teaspoon, spinning at hundreds of revolutions per second, wrapped in magnetic fields 1 trillion times stronger than Earth's. If the star was more massive still, the core collapses past even the neutron star stage. The neutron degeneracy pressure that holds up a neutron star fails, and the core becomes a black hole, a region of space where gravity is so extreme that nothing, not light, not information, not time itself as we understand it, can escape. The sun will never experience any of this. It is too small, too gentle, too ordinary. And in cosmic terms, that is a blessing. Planets orbiting massive stars are sterilized by the supernova. Everything within light years is bathed in lethal radiation. The star's death is not just its own destruction, it is the destruction of its entire neighborhood. The sun's quiet death, by contrast, leaves the outer solar system largely intact. The planets survive, the moons survive, the potential for future life survives. The sun's modesty is its gift. Now consider the opposite end of the scale. stars less massive than about 0.8 solar masses. These are the red dwarfs. They are the most common stars in the Milky Way, making up roughly 75% of all stars. And they will outlive everything. Red dwarfs are miserly. They burn their hydrogen so slowly that their lifetimes are measured not in billions of years, but in trillions. Proxima Centauri, the nearest star to the Sun, is a red dwarf with about 12% of the Sun's mass. It will still be burning 4 trillion years from now, long after the Sun has become a white dwarf. Long after the white dwarf has cooled into a black crystal, Proxima Centauri will still be shining. And red dwarfs have another advantage. They are fully convective. In the Sun, only the outer 30% or so of the star undergoes convection, the process by which hot material rises and cool material sinks, mixing the gas. The core, where fusion occurs, is not connected to the outer envelope. Helium ash builds up in the core because there is no mechanism to mix it with the fresh hydrogen above. The fuel in the core is consumed, while vast reserves of hydrogen in the outer layers remain untouched. Red dwarfs do not have this problem. Their entire volume convects. Hot material from the core rises to the surface. Cool material from the surface sinks to the core. Hydrogen is mixed throughout the star. Nothing goes to waste. A red dwarf uses virtually 100% of its hydrogen fuel, compared to the Sun's roughly 10%. This is why they last so long. And when a red dwarf finally does exhaust its fuel trillions of years from now, it does not become a red giant. It is not massive enough. It simply fades. It contracts directly into a white dwarf without the dramatic expansion, the planetary nebula, the violent death throes. A quiet fade to a quiet ember. The universe in the far future will belong to the red dwarfs. Long after every sun-like star has died, long after every massive star has exploded, the little ones will still be burning. The last natural light in the universe will come from a red dwarf. The last warmth will come from a red dwarf. When historians of the far future, if any exist, look back at the era of the universe when the sun shone, it will seem like a brief, bright flash in an epoch dominated by the slow, steady glow of tiny stars. There is one more type of stellar death that deserves mention because it involves white dwarfs directly. A type Ia supernova occurs when a white dwarf in a binary star system accretes material from a companion star. Gas from the companion falls onto the white dwarf's surface, adding mass. If the white dwarf's mass is pushed past the Chandrasekhar limit, 1.4 solar masses, the electron degeneracy pressure fails. The star collapses and detonates in a thermonuclear explosion so consistent and so predictable that astronomers use type Ia supernovae as standard candles to measure distances across the universe. The explosion completely destroys the white dwarf. No remnant, no neutron star, no black hole, total annihilation. The Sun's white dwarf, alone and isolated, will never face this fate. It has no binary companion to feed it. It will cool in peace. But in binary systems across the galaxy, even Death Stars can die again. The Sun's quiet death is almost merciful compared to what happens to the monsters. But there is one more piece of the story. What the Sun leaves behind is not just a corpse, it is a gift. Chapter 13. Stardust, the Sun's gift to the future. Every atom of carbon in your body was forged inside a star, not the Sun, a star that died before the Sun was born, a star that lived and burned and exhausted its fuel and expelled its processed material into space billions of years before our solar system even existed. That material drifted through the galaxy as gas and dust, accumulated in a molecular cloud, and when that cloud collapsed under its own gravity roughly 4.5 billion years ago, it formed the Sun, the planets, and everything on them, including you. You are made of dead stars. This is not poetry, it is nuclear physics. The carbon in every cell of your body was produced through the triple alpha process. the same reaction that ignites during the helium flash. 3 helium nuclei fused into one carbon-12 nucleus inside the core of a star that no longer exists. The oxygen you are breathing right now was created during helium shell burning, the fusion of carbon with an additional helium nucleus to produce oxygen-16. The nitrogen in your DNA was forged through the carbon-nitrogen-oxygen cycle, a catalytic chain of reactions that occurs during hydrogen burning in stars, slightly more massive than the Sun. The calcium in your bones, the iron in your blood, the phosphorus in your cell membranes, all of it was synthesized in stellar interiors and scattered into space by stellar winds and explosions. The Sun will return the favor. During the planetary nebula phase, the Sun will expel roughly half its mass into interstellar space. This material is not pristine hydrogen and helium. It has been processed, modified by billions of years of nuclear reactions, enriched with elements that did not exist when the Sun first formed. Carbon, nitrogen, oxygen, and traces of heavier elements dredged up from the interior by convective mixing during the asymptotic giant branch phase. All of this will be injected into the interstellar medium. And the planetary nebula is not just a cloud of hot gas, it is a chemical factory. As the ejected material expands and cools, complex molecules begin to form. Atoms that were too hot to bond inside the star find partners in the cooling nebula gas. Carbon atoms link together in rings and chains, forming polycyclic aromatic hydrocarbons. These are among the most common organic molecules in the universe, and they are the building blocks of the chemistry that leads to life. They have been detected in interstellar clouds, in meteorites, in comets, and in the atmospheres of distant planets. The Sun's death will produce more of them and scatter them through the galaxy. Dust grains form in the nebula winds, microscopic particles of silicates and carbon compounds condensing out of the cooling gas like snowflakes forming in a winter sky. These grains are the seeds of rocky planets, the very material that formed Earth 4.5 billion years ago. The silicate rock of the mantle, the iron of the core, the water of the oceans, came from dust grains that formed in the dying breath of a previous generation of stars. The Sun will contribute its own grains, its own seeds, its own raw material for future worlds. This is the great cycle of stellar evolution. Stars form from clouds. Stars burn. Stars die. Stars expel their processed material back into the interstellar medium. That material mixes with the existing gas and dust, enriching it with heavier elements. New clouds form, new stars ignite, new planets coalesce. And on some of those planets, the conditions are right for chemistry to become biology, for atoms to arrange themselves into molecules that can replicate, for life to begin. Each generation of stars is richer in heavy elements than the last. The first stars in the universe, formed from the pristine hydrogen and helium left over from the Big Bang, contained no carbon, no oxygen, no iron, no silicon. They were massive, short-lived, and when they died, they seeded the universe with the first heavy elements. The next generation of stars formed from this enriched material and produced even more, and so on, generation after generation, each stellar life cycle, adding to the cosmic inventory of elements. The Sun is a third-generation star, roughly. It formed from material that had already been processed by at least 2 previous generations of stellar evolution. The iron in Earth's core was forged in a supernova that predates the solar system. The water in your body contains oxygen atoms that were synthesized in a red giant that died before the Sun was born. You are not just made of stardust. You are made of recycled stardust. Stardust that has been through the furnace more than once. Now look forward. Billions of years from now, the Sun's planetary nebula will have dispersed. Its atoms will be scattered across light years of interstellar space, mixed into the vast reservoir of gas and dust that permeates the Milky Way. Over millions of years, some of that material will accumulate in a new molecular cloud. the cloud will grow. It will become dense. And, at some point, a region of the cloud will collapse under its own gravity, fragmenting into clumps that will become new stars. A new star will form, carrying in its chemical composition the fingerprint of the sun, carbon atoms from the sun's core, nitrogen from its hydrogen shell, oxygen from its helium-burning phase. These atoms will be part of the new star's birth cloud, incorporated into the new star and its planets. And on one of those planets, if conditions are right, those atoms might become part of something alive. The carbon that was once inside the sun might end up inside a cell on a planet orbiting a star that does not yet exist. The oxygen that was processed through the sun's nuclear reactions might one day be breathed by a creature that cannot imagine the star its atoms came from. The sun's death is not an endpoint. It is a transfer, a handing over of material from one generation to the next, a gift wrapped in a glowing nebula left on the doorstep of the future. Death, in the cosmic sense, is not an ending but a transformation, a recycling of matter on scales we can barely comprehend. Every star that has ever died has contributed to the universe's growing library of elements. Every planetary nebula that has ever faded has seeded the next generation. And the sun, when its time comes, will do the same. The atoms scatter, new stars form, the cycle repeats, but step back far enough to see the whole arc of the universe, and a deeper question emerges, one that physics alone cannot answer. Chapter 14. The Meaning of a Dying Sun. Every star that has ever shone will eventually go dark, every single one. The massive blue supergiants that blaze with the light of a million suns. The steady yellow dwarfs like ours that burn for billions of years. The tiny red dwarfs that will outlast everything else by trillions of years. All of them, 100% of them, will exhaust their fuel and go silent. There are no exceptions. There is no star in the observable universe that will burn forever. And the era in which any stars shine at all, the luminous epoch of the cosmos, is a vanishingly small fraction of the universe's total future. If the universe lasts for the timescales we have been discussing tonight, trillions and quadrillions, and numbers so large they require exponents to even write down, then the period during which stars illuminate the void is a brief, bright flash at the very beginning, a candle lit in the first second of a very long night. We live in that second. We are the light, or at least, we exist because of it. The sun's death is not unique. It is not a tragedy that befalls our star alone, while others burn on in eternal glory. It is the universal fate. Every star system in the Milky Way, every star system in Andromeda, every star system in every galaxy in the observable universe will go through its own version of what we have described tonight. The details differ. The timescales vary. But the outcome is the same. Light becomes darkness. Heat becomes cold. Motion becomes stillness. And yet here we are, alive, conscious, aware, made of atoms forged in the hearts of dead stars, assembled by 4 billion years of evolution into organisms that can look up at the night sky and contemplate the death of the very star that gave them life. That is not a trivial thing. In a universe that trends relentlessly toward disorder and darkness, the fact that matter organized itself into beings capable of understanding the universe is extraordinary, not in a supernatural sense, in a statistical sense. The odds against your existence are so immense that they make the timescales of stellar evolution look modest. Human civilization is roughly 10,000 years old. The sun has about 5 billion years remaining on the main sequence before it begins to die. 5 billion years. That is 500,000 times the entire length of recorded human history. We worry about the next decade, the next election, the next quarterly earnings report. The sun's death operates on timescales 500 million times longer than all of recorded history combined. The disparity is so extreme that it reshapes how you think about permanence. Nothing built by human hands will survive the sun's death. Not the pyramids, not the Great Wall, not the golden record on the Voyager spacecraft, not the footprints on the moon. All of it will be consumed, dissolved, scattered, or erased by the same geological and astrophysical processes that will unmake the Earth itself. In the very long run, no artifact endures, no monument persists, no record survives. But the atoms will. The atoms that make up your body right now will still exist when the sun is a white dwarf. They will still exist when the white dwarf has crystallized into a diamond. They will still exist, scattered across interstellar space or locked into new planets around new stars, when the sun's black dwarf sits cold and dark in an empty universe. The atoms are eternal, or as close to eternal as anything in physics gets. They will be rearranged, recombined, recycled, but they will not be destroyed. The question then is not whether you will be remembered. In the very long run, you will not. No one will. The question is whether the pattern of consciousness that you represent, the capacity for awareness, for wonder, for love, for understanding, will emerge again, somewhere, in some form, at some point in the future. And the honest answer is that we do not know, but the ingredients will be there. The carbon, the oxygen, the nitrogen, the water, all of it will be available, scattered through the galaxy by the sun's death, waiting to be assembled by gravity and chemistry and time into whatever comes next. Knowing the sun will die does not diminish the present. If anything, it sharpens it. Every sunrise you have ever seen is powered by a thermonuclear reaction that is one day closer to ending. The warmth on your skin is hydrogen becoming helium, and that hydrogen is running out, 600 million tons per second, and the supply is finite. Every moment of warmth, every photon of light, every calorie of energy that sustains you is drawn from a reservoir that is slowly emptying. Earth's biosphere has roughly 1 billion years of complex life remaining. That is our window. 1 billion years to do whatever it is we are going to do, to grow, to learn, to reach beyond this planet, to become something that can survive the death of its star, or to remain what we are and accept the consequences. The choice, ultimately, is ours. The sun does not care. It will brighten and swell and die, regardless of what we do. The question is what we will do with the time we have. The sun's death is the ultimate reminder. Nothing lasts. The rock is patient, the stars are temporary, the light is borrowed. And because nothing lasts, everything matters. Every discovery, every act of kindness, every moment of understanding, every attempt to reach beyond ourselves and make something that outlives us. Not because it will survive forever. It will not. But because the making of it, the reaching, the trying, is what consciousness does when it knows the clock is ticking. The Egyptian pharaohs carved their names into stone because they wanted to be remembered. The builders of Göbekli Tepe created something so remarkable that it survived 12,000 years of burial. The people who told the first myths about the sun, about the god who rides a chariot across the sky, about the fire that gives life and takes it away, they were trying to understand the same thing we are trying to understand tonight. What does it mean that the light will go out? And what should we do while it is still burning? The sun will die. Everything you have ever known exists in its light. And the most extraordinary part of this story is not how the sun ends. It is that you were alive to wonder about it. If you enjoyed this deep journey through the life and death of our sun, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell us in the comments, what do you think humanity should do with its remaining billion years? Should we try to escape? Should we accept the inevitable? And what mysteries of the cosmos should we explore next? These are not just questions for scientists. They are questions for all of us, because the sun is still burning, and we are still here. Thank you for listening. We will see you in the next journey.